Hello, data science students. I hope you're all doing well, staying happy, healthy, and safe. Today, we're going to be talking about polynomial and logistic regression. So, leading off of our conversation last time about linear regression. Before we get into that, let's talk about something maybe a little less serious. So, according to the interwebs, a lot of folks during this time of quarantine and isolation have started doing what's been dubbed quarantine baking. So a lot of people started like cooking stuff, which is really cool. You know, it's nice, it's fun. I personally like it. I love cooking, but I'm not a baker. And lots of baking going on out there. And when it comes to cooking, I think it's very artistic. Like you can get flavors together and construct interesting profiles, and it's really cool. But baking is a different story. Baking is essentially a chemistry experiment, you know? It's all about chemical reactions between this ingredient and that ingredient. If you don't have them just right, you won't get rise or spread or the texture you're looking for. It's really a different from cooking. And sometimes, especially when you're in quarantine, you might not have the ingredients you're looking for. Well, turns out, since it's like chemistry, if you can find something that has similar chemical properties to the thing that you're missing, you might just be able to substitute something for what you're missing. And here's some interesting substitutions. Say for like eggs, you can substitute applesauce or vegetable oil, or the really interesting one, flaxseed. Flaxseed will serve the same chemical purpose as eggs. It's mind-blowing. And there's other things you can substitute, like say butter. You can substitute shortening or oil, or substitute cream of tartar and baking soda for baking powder. And what's this one? Oh, corn syrup. You can get white sugar and water. I mean, it's some easy stuff. So if you're interested in these kind of substitutions, you can probably Google image search this and find what you're looking for. But this is actually important for today's lecture too. Actually, probably is going to be more important in the second part of today's lecture as opposed to the first part, but we'll see where we get. Okay. Also, Challenge 5 has been posted for a while, but just recently, as of our linear regression lecture, you just learned the stuff that you need to do to make this happen. So this assignment is actually going to be quite similar to the weather station assignment you had earlier in the semester, where you had to look at data coming from radio transmitting stations and see which ones were functional and which ones were just noise. So in this setup, in this assignment, you're taking the role on as a person contracted by SETI, the Search for Extraterrestrial Intelligence. And you're looking at radio data. And specifically, you've been given data for 5 frequencies, and you're to look for the frequencies that have structure and the frequencies that don't. And the difference between this guy, so here's an example of one of the structured frequency changes, or structured signals for a given frequency that you might see in your data. One of the differences between this assignment and the previous assignment is before, I let you figure out which was structure, which was noise, using whatever method you wanted. You could look at the data and eyeball it. You could plot it in Excel and then do your programming assignment. You could just guess, any way to figure out which one was the proper frequencies was acceptable. Not this time. This time around, your program is going to have to figure it out on its own. Now that sounds daunting and scary, but actually it's not as scary as you might think. Think back to our lecture on linear regression and how I talked about all the statistical methods that we've learned being sort of items in a toolbox. Think of them in that way. And these tools are things that you can use to build more complicated and more interesting things. So you might be surprised how much mileage you can get out of using one of your standard statistical methods. Say, your means, your standard deviations, your variances, your correlations, to figure out which one of the patterns or which one of the frequencies in your data set have structure and which of them are just noise. Okay, so you have specifically you'll have 2 different patterns hidden in your data set. And what I want you to do is to actually produce a plot that looks something like this. Plot each of the different frequencies as a different color. And I also want you to plot linear regression and a polynomial regression for each of the structured data. So in this example, the blue line is our polynomial regression, and the red line is our linear regression. Now, NumPy has linear and polynomial regression functions built into it. However, for your linear regression, you can't use them. You have to use the method that we talked about in our previous lecture. So you have to write your linear regression code from scratch. But your polynomial regression code, you can actually use what we're going to go over today with NumPy. So using NumPy's built-in polynomial regression functions. And on that note, polynomial models. We've talked about these a bit before, and we talked specifically that they come in varying degrees, and they follow a very specific formulation. Formulation where some y value equals some constant times an x value raised to a power plus some constant times an x value raised to a power, so on and so forth, where the x raised to a power corresponds to 0 up until the number of degrees you have in your model. So you could have a polynomial model of k number of degrees, and it'll look something like this. We can look at this and pretty quickly see that this can be reformulated easily as just a summation. So in the summation, we've got a series of x values, a series of y values, and we're incrementing from 0 until k degrees. And then we've got this constant out here that our I raised to whatever our iteration degree is. That's the one thing we don't know. So the one thing that we don't know in the polynomial model is the constant that's associated with each one of these terms. We know what the degree is because, well, we've specified the degree, and at each step of this summation, it's going to be 0, 1, 2, all the way on up to whatever degree that we've specified. So what we're wanting to predict is actually the constant that goes in front of the x. And fortunately, and I've put a big orange star up here in front of everything on this slide, so you know this is the important slide. You're going to be able to use NumPy's Polyfit function to predict these. So the Polyfit function takes 3 parameters: a list of the x values in your training data, a list of y values in your training data, and your training data being the data you're using to build your polynomial model. And then the third parameter is the degree of the model. Now what this returns is what we call our regression parameters. These are those constants, those c values that are in front of your x component in your polynomial equation. Now, once you've got those constants, you can then, just do the math and do your polynomial modeling from there. But NumPy has that built in for you as well with the polyval function. So NumPy or np.polyval, you pass in the first parameter will be the constants, the list of regression parameters that come out of Polyfit. And then x is the list of x values that you want to do your regression for. And this returns a list of predicted y values that are associated with all of the x values in this list. Now, this x and this x don't necessarily have to be the same thing. Matter of fact, usually don't want them to be the same thing. Keep in mind, one of the strengths of modeling is that you can predict values in between the values that you've already collected, in between the points of your training data. So let's look at how different degrees of a polynomial model might look trying to model a set of data. This is real data that we collected in a user study a few years ago, looking at how people perceive orientations, angular orientations in the real and virtual worlds. And you see some obvious patterns looking at this. You see a nice kind of like sine wave-y kind of zigzag. So if we try to model this using a 0-degree polynomial model, what we get is a horizontal line going through the center of our data set. If we up that to a 1-degree polynomial model, we get a slanted line going through our set of data. If we do a 2-degree polynomial model, we get a bend going through our data. If we do a 3-degree polynomial model, we get 2 bends. If we do a 4-degree, we get 3 bends in our data. And you can see at about 7, we start getting something that's fairly close to the pattern we're seeing in our raw data. But if we get it higher, say we bump it up to 15 degrees, we're pretty darn close to replicating the data that we trained the model with. Seems like a great plan. Let's bump it up even higher. If we do a 50-degree polynomial model, we end up being able to replicate our raw data values almost exactly. And remember, we've talked about this before, that hyperfitting your models isn't necessarily a good thing, and that it can actually cause more problems than you want. But why is this? This seems like it's actually a good idea. Well, here's the problem, and the problem comes in between our data points, so to speak. As they say, the devil is in the details. Remember that the raw data you're collecting isn't actually what you're interested in. You're interested in modeling the thing that produced your raw data. All data is an echo of something else, indirect, distorted, and noisy. So when we're doing our modeling, we're not trying to replicate our raw data. We're trying to replicate the function that produced them. So by hyperfitting our model with like an inflated degree polynomial, we're reproducing the training data, but we're not reproducing the model or the function that produced that training data. So what we want to do is actually model the thing that's generating the patterns in our data, not the data itself. Now, different kinds of modeling techniques are more appropriate for some kinds of data than another. For instance, we talked a little bit about doing image reconstruction earlier in the semester. Polynomial modeling might not be the best thing for that, mostly because polynomial models work best for things that are somewhat continuous, with not with hard edges and large sudden changes. And if we look at this, we've got very hard lines across parts of this architecture. We've got strong contrasts between the foreground and the background and the light and shadow. Something like this, polynomial modeling isn't going to work well for. However, for something like this, and this doesn't look too good, does it? Let me tell you what this is. This is actually image data taken through a lens. So a camera is looking through a lens in a VR display, and on the other side of that, we're displaying a picture of a grid of a known size. So we know what the grid should look like, and we're measuring, using a camera, what's coming out the other side of the lens. So lenses, if you ever look through a magnifying glass, you've probably noticed that what you're seeing looks okay in the middle and then starts bowing outward or becoming distorted towards the edges of the lens. We have that same problem in virtual reality when we put lenses in our headsets. And so we want to measure those distortions. And an easy way to measure and model those distortions is using polynomial modeling. And this is actually really advantageous because lens distortions are fairly continuous. And polynomial modeling is a very robust modeling technique. So if we look at this data right here, it actually looks kind of bad. I mean, we've got a lot of data points. We've got some weird artifacts like the camera, probably because of a glare or something, couldn't see the pixels in this corner. There's some data missing here, there's data missing here, there's some weird little streaking artifacts all throughout the data. But if we have enough, what we can do is then use our polynomial regression technique to predict what values should fall in each of these empty spaces, in each of these gaps, and even correct the noisy data that we've already collected. And so this right here can be modeled, and a very clean pattern can come out the other side. And it's a fairly robust technique, because you can even have even worse data. This is another set of lens calibration data that we collected, and we got a very good recreation of the distortion patterns inside of that lens just from this data. So as long as the transitions within the data you're modeling are somewhat smooth and continuous, polynomial modeling tends to work really well. However, not everything exists on a gradient. Sometimes we want to model state changes. There are certain things for which there isn't a 50% here or a 40% there, and it's just you are one thing or you're something else. And you can kind of think of these things as like the difference between employed and unemployed, difference between dead and alive, difference between old enough to buy alcohol versus not old enough to buy alcohol. That's not saying a thing about consumption. That's about the legal limit for buying versus being on the other side of the legal limit for buying. Whether or not you bought a product online or you didn't buy a product online or something like that. these things don't have a 50% I bought the product or a 40% dead or alive. You're either one state or the other. So modeling these state changes is actually really important as well. And I've baked up some data that we can look at that's going to look at the relationship between age and alcohol consumption. And so let's pretend that we went out and gave a survey to people of all ages, say maybe a couple hundred people, and asked them the one question: answer yes or no, have you consumed alcohol? And by the way, this data I'm about to show you is synthetic. I've made it for this example, and I've looked up the real data on age and alcohol consumption, and it is too depressing to even think about it. It's crazy. Alcoholism starts incredibly early, so be aware and be mindful. But for our example, let's say this was our survey data. What we found is that there were a lot of no answers and there were a lot of yes answers. And we're seeing a very distinct pattern here, that there's a clustering of no responses towards lower ages and a clustering of yes responses towards higher ages. Now, notice though that this axis doesn't say yes or no, so to speak. It's 0 to 1 and labeled as the probability of a yes response. So sometimes our state changes don't necessarily have a numeric value associated with them. Like bought a product versus not bought a product, there's no number representing whether or not that happened. So what we have to do is sometimes use something called a pseudo variable. And that's taking something that's non-numeric and mapping it to a numeric value. And this is often done between 0 and 1 for like binary responses, like yes or no's, bought, not bought, dead, alive, employed, unemployed, those kind of things. So in this case, we've mapped 1 to yes and 0 to no. And this is going to end up becoming very convenient for us because this ends up making an implicit probability value. So 0, the no response, being the probability of a person having answered yes. So if they've answered no, there's a 0 probability of them answering yes. Similarly, if they answered yes, there's a 100% or a 1 probability of them answering yes to the question. And for each age group, you can average the yes and no responses together to build up a probability of how many people in each of these groups answered yes or no to the question. So this actually ends up being very convenient for getting an implicit probability within our group of data. So let's say we wanted to model this. No, one thing I want to say before we get to that is recall from our earlier lectures that for most of the statistical analyses we do, we're not actually interested in the individual because we can't really well describe an individual from a lot of our statistics. We can describe populations very well with our statistics. And so even though an individual can't have a 50%, yes or no, a population can have a 50% probability of having answered yes or no. So when we do a model of a set of data like this, we're not trying to describe whether or not a single person has said yes or no to a question. We're trying to describe the probability that that person in the population has said yes or no to the question. So a portion of the population will have answered one way and a portion of the population would have answered the other. So if we try to model this relationship with our linear regression, we end up getting something that doesn't make any sense. Almost a vertical line shooting up right through the middle of 21, with below 21 having negative probabilities of having done something, and above 21 having hyper probabilities beyond 1 of doing something. Now these are nonsensical values. You can't have probabilities greater than 100%. You can't have probabilities in the negative. So linear regression, and if we zoom out, it becomes even more exaggerated how ridiculous this is. Linear regression can't model this state change relationship. So let's try to use a more sophisticated modeling technique. Let's see our polynomial modeling. Now we have something here that actually ends up making a little more sense, but still doesn't quite work. We end up with a smooth transition between our yeses and our nos, all centering very close to 21. But then we end up with oscillations between negative and positive probabilities below the age of about 15, and then hyper probabilities and our our early to mid-20s and less likelihood in our 30s, and that doesn't make any sense, you know. So this is getting closer to modeling the transition between one state and another, but it's still not really giving us what we want. What we want is a model that's going to provide us with a smooth transition that approaches 0 probability on one end and approaches 100% probability or 1 on the other end, and gives us a smooth transition in between that ends up being the relationship between the probability of yeses for one group and no to nos from that same group. So giving us a smooth transition of probabilities for a given population between this state and the other state. And so this is what we call a logistic regression. Now we see this in a lot of different places, and in particular we use it in psychology and perception research a good bit. In this field we call it the psychometric function. And it represents the state change from one thing to another thing, with the point of subjective equality, as we call it, being that 50-50 mark. So when you cross the boundary between 50% likelihood of a yes response or no response. And so right here is where we're going to wrap up our conceptual discussion of logistic regression. We're going to come back with a second video talking about the actual implementation and the mathematics behind doing logistic regression. So we're going to wrap it up right there, and I hope you're all doing well. Again, hope you're all staying happy, healthy, and safe, and washing your hands. If you need any help or have any questions, please come see me in my office hours. You can go to my Ole Miss website or my personal website, and there's a giant blue button on the front page. Click it, enter your email address, and you'll be connected to me in a Skype session. Again, use your official University of Mississippi email address. And yeah, if you have any questions, please let me know. And otherwise, I will see you in cyberspace.